Hi, I'm Gary Rubenstein. This is a rehearsal for a presentation I'm going to do for the NCTM in Boston. It's about the non-European roots of math topics. The title of the presentation is What? You mean my ancestors helped invent math? And it's about how a lot of math was invented and developed in China, in India, in the Middle East, and in Egypt. And I'm going to go through some topics that I think would be of interest to high school teachers and students of high school students, middle school students, things that can complement the regular curriculum. So some of the topics are the same topics that we study nowadays in elementary school: multiplication and division, fractions and decimals, solving algebraic equations, linear, quadratic, calculating square roots, cube roots, things like pi, area of circles, and things with triangles, and also some stuff in number theory. The two books that I used primarily, one was called The Crest of the Peacock, and that was a pretty well-written book that was somewhat easy to follow. Then there was this book by Victor Katz, I think it's called Math of those countries, Mesopotamia, Egypt, China, India, and that book is a pretty big undertaking, like an encyclopedia. If you had those two books, those would keep you busy for a pretty long time. So if you're wondering about studying more about these topics, you can find those books. I also did a lot of searching on JSTOR for articles about some of these topics. So the first country is Egypt, and in Egypt, way back 1600 BC, they were doing some good math there, and there's the main document, the main source material, something called the Rhind Papyrus, and it has about 90 different problems doing different sorts of math. The way they multiplied was interesting. To multiply numbers together, the only skills they needed were how to double numbers and how to add numbers. So in this case, to multiply 23 times 21, they made this chart. 1 times 23 is 23, then they double it. So 2 times 23 is 46, then they double that. 4 times 23 is 92, they double that. 8 times 23 is 184, so they just keep doubling because that was a skill they had. And then they look on the left-hand column and see which of those numbers add up to 21. And in this case, it's 1 plus 4 plus 16. So you add the corresponding numbers on the right-hand side, 23 plus 92 plus 368 to get 483. And if you teach this method in class, it can bring up the discussion about, is it possible that it's not going to work? You know, is there any sort of number that you want to multiply 23 by where somehow these powers of 2 would not add up to the number you want them to? And I think that would be an interesting discussion. It turns out that it is always possible to add up powers of 2, one of each, to get any integer. Division was a lot like multiplication. So dividing 483 by 23, you'd actually produce the exact same chart: 1 times 23, 2 times 23, 4 times 23, and so on until you got to, you wouldn't do 32 times 23 because it would already be bigger than the thing that you're trying to, achieve, 483. So once you get to the biggest number that's under 483, which is 368, again, you look through for numbers that add up to 483. And that's an interesting discussion about how do you maybe do that. I mean, one way is to subtract the largest number that you have, which is 368, from 483, and then keep subtracting the largest one. It brings up the question, is there always a way to do this? And if so, is there a method? So this is a neat little method because it only has adding and doubling in it. In this case, the answer does become 21. Hold on. So sometimes when in a division problem it didn't work out evenly, like 15 divided by 4. So you start doing 1 times 4, 2 times 4 is 8, and 4 times 4 is 16. It's already too big. So to deal with that, they had to use fractions. So they start dividing 1 by 2 and get 1/2 times 4 is 2, and then divide that by 2. So they can, dividing a fraction by 2 is pretty easy because you just have to double the denominators. And now you have 4 plus 8 plus 2 plus 1 is 15, and the answer is 1 plus 2 plus 1/2 plus 1/4, which they would write as 3 plus 1/2 plus 1/4. Back in those days, their fractions were what are known as now Egyptian or unit fractions, and they have to have 1 in the numerator, and they can't be any repeats, so you wouldn't have 1/4 plus 1/4 plus 1/4. You'd write it as 3 plus 1/2 plus 1/4. The only fraction they had that didn't have a 1 in the numerator was 2/3, which was a special fraction for them. Otherwise, it had to have numerators of 1, and if you wanted to put multiple things together, you had to use different unit fractions. So you see 3/4 there would be written for them as 1/2 plus 1/4, or really just 1/2 and then 1/4 next to it. 3/5 would be written as 1/2 plus 1/10. Something about these unit fraction decompositions is that they are not unique. So there might be different ways of doing it, and kids could mess around, figure out different ways to add up fractions to get other fractions, where the fractions have to have this restriction of 1 in the numerator and have to have no repeats of the same fractions. There's been some speculation about what the benefit is of not using the same unit fraction more than once. Several of the questions in the Ramanujan papyrus are about dividing loaves of bread among 10 men. So they divide 1 loaf among 10 men, 2 loaves, 3 loaves. Some of them get some pretty interesting answers, but dividing 6 loaves among 10 men, nowadays we'd say each man gets 3/5 of a loaf, although they would say 1/2 and 1/10. There's a benefit here, because let's say you really had 6 loaves of bread and there were 10 men that wanted to divide them. If you say each man gets 3/5, you have to split the 6 loaves up like this, where you cut each of the 6 loaves into a 3/5 slice and a 2/5 slice, and you can give 6 of the men a 3/5 slice. But now you've got these 2/5 slices left over, so you give 4 of the men 2/5 slices, and you take the other 2 2/5 and cut those and cut those up into 1/5. And although they each got 3/5 of a loaf, they may not be happy about it. Maybe some of the guys didn't want a small piece and a medium piece. They wanted the same big piece, and maybe they even didn't believe that they got the same amount of bread as the other person. So if instead I call my 3/5 1/2 plus 1/10, I actually can give everybody 1/2 a loaf and 1/10 of a loaf. And not only does everybody get the same amount, but everyone gets the same amount, the same way, and nobody's suspicious or jealous of one of the other people. So there might have been a practical reason for doing it this way. To multiply fractions using that whole doubling method that you saw before would require being able to double fractions. So they had a lot of charts in Egyptian math, and here's a nice chart about the 2 over n chart. So you can see that 2/3 is equal to 1/2 plus 1/6, 2/9 is 1/6 plus 1/18, 2/5 is 1/3 plus 1/15. These are all ways of breaking up 2 over numbers, going up to 2 over 101. All the odd denominators. You don't do the even denominators, because like 2/4 is just 1/2, 2/6 is just 1/3. But when you have the odd denominator, you have to, in order to double these fractions, you're going to need to turn this like 2/9 into 1/6 plus 1/18. This chart, they tried to minimize the number of fractions, so there's a lot of times just two different unit factors adding up to each of the doubles. They also try to keep the numbers as small as they can, but some of them you really can't avoid, like 2/79 is 1/60 plus 1/237 plus 1/316 plus 1/790. That was the best they can do with trying to keep the numbers, denominator small, and the number of terms being small. So if I wanted to multiply 2/3 plus 1/30 by 10, it would look like this. The first row would be 1 and 2/3 plus 1/30, and then we would double for the second row. 2/3 doubled is 1 and 1/3. 1/30 double, to double a fraction with an even denominator, you just divide the denominator by 2. Then we double it again, so now we have 4. 1 times 1 is 2. 1/3 times 2 is 2/3. They did have a fraction for 2/3. But for 1/15, you'd have to go back to that chart. 1/15, according to this chart, is 1/10 plus 1/30. So that's why their 1/15 when doubled became 1/10 plus 1/30. Then to get the next row, they double the 2 to get 4. They double the 2/3 to get 1 and 1/3. They double the 1/10. It's got an even denominator to 1/5. They double the 1/30, even denominator to 1/15. So they only had to use the chart once so far. 1 plus 2 plus 8 is 10. 5 plus 1/3 plus 1/5 plus 1/15. Now they could have left the answer just like that, but back then they were really good with knowing when this combination of fractions equaled another combinations of fractions. So 1/3 plus 1/5 plus 1/15 actually equals 3/5. Remember, 1/3 plus 1/15 in the second row was how they got. Hold on. The 1/30. Sorry. In the I got myself confused here. But moving on. 1/3 plus 1/5 plus 1/15 is actually. Oh yes, I see. Back in this chart, 2/5 is 1/3 plus 1/15. So when they see in that 8, that row with the 8 in it, 1/3 plus 1/15, they recognize that instantly as equivalent to 2/5, and then they have this other 1/5. So basically, this is 3/5. But 3/5 has a simpler fraction decomposition, which is 1/2 plus 1/10. So they'd write the answer this way. So they got really good with these fractions and recognizing combinations that equaled other combinations to make their answers efficient. They had algebra in Egypt, and again, this is back in like 1600 BC. So if they wanted to answer this question, x plus 1/7 x equals 16, they would first take a guess, and they would guess the most convenient number possible, which was 7, because 1/7 of 7 is an integer. Then they test it, and the test is 7 plus 1/7 of 7, 16, and the answer is no, it's 8, not 16. So then they would adjust their answer. They'd say, well, I got 8, I wanted 16, so if I divide 16 by 8, I get 2, and that means my answer is off by a factor of 2. So I just multiply 7 times 2 equals 14, which is the answer to this question. Now to combine multiplying, dividing, and false position with one last example from Egyptian math before we move on to the next culture. X plus 1/7 x equals 19. We still start off with 7, and we get an answer of 8, not 19. Now this gets much more complicated because we need to know how much is our number, by what factor is our number, answer, or guess of 7 off by. So for that we need to divide 19 divided by 8. That's going to be, a process. And then we have to multiply 7 by whatever that answer is. So this chart on the left says that those x's are like the check marks. This is the process of dividing 19 divided by 8. 1 times 1 times 8 is 8, double it, 2 times 8 is 16. Next one's going to be bigger than 19, so we start going to the half and the quarter and the eighth. And we find out that 19 divided by 8 is 2 plus 1/4 plus 1/8, nowadays known as 2 3/8, but back then 2 1/4, 1/8. Now that's the factor that our original guess was off by. So now we multiply 2 plus 1/4 plus 1/8 by 7, which we do by multiplying, doubling it to get 2 times it, and then doubling it again to get 4 times it. 1 plus 2 plus 4 is 7. And the answer to this algebra question is 16 and 5/8, back then written as 16 plus 1/2 plus 1/8. So that's what I wanted to say about Egyptian math. There's an entire book called Math in the Time of the Pharaohs that really goes into it, and I think you'll be impressed with the way they worked with their fractions and the ability they had that we don't have nowadays of recognizing, different combinations of fractions that equal to other combinations of fractions, or how did they figure out this combination. And it was very cool. So that takes care of Egypt. Moving on to the next culture. The next culture they generally call Babylonia, which is in the Middle East now, mainly Iraq in that vicinity. They found a lot of, so in Egypt they have the papyrus, which actually survived fairly well, considering it's from like 1600 BC. In Babylonia, they put their stuff on stone tablets, and that stuff really survived, and we have all kinds of tablets of all kinds of things that they've found. So in Babylonia, they had Babylonian math, they had a base 60 system. The Egyptians didn't have much of a number system in that way, but base 60, the ones place is still ones, and what we think of as the tens place is now the 60th place. And they didn't have like 60 different digits within their base 60. They had kind of like a base 10 system. They had a sort of base 10 system within their base 60 system, so it gets a little confusing, but for our purposes, nowadays we write it out this way, where we put a little space between the 60s place and the ones place. So this number 159 is really 119, because, or in base 10 is 119, because it's 160 plus 59 ones is 119, whereas the number 20 in base 60, that's 120, because it's 2 times 60 and no ones. And the question is, where else have you ever seen 159 plus 1 equals 200? And the answer is time, that we still use in base 60, and also degrees and minutes are also in base 60. Base 60 is actually very convenient for decimals, or they nowadays we call it like the sexagesimal system if you're using your base 60. But like in base 10, 0.25 is that 2 represents 2/10, the 5 represents 5/100. In base 60, we usually put this little semicolon here. So 730 is 7 over 60, and the 30 is 30. That second place is not the hundredths, but it's the 3600ths. And there is a benefit of base 60 over base 10, which is that you don't have as many repeating decimals. In base 10, most things repeat. The only things that don't repeat are things that have only factors, numbers that only have factors of 2 and 5. But with base 60, you get fewer repeating decimals, so 1/2 is 0.30, 30/60ths in base 60. 1/3, which requires repeating decimals in base 10, is actually just 0.20, 20/60ths. 1/4 is 0.15, 1/5 is 0.12. Those things both are not repeating in base 10 either, but 1/6, which requires repeating decimals in base 10, does not require it for base 60. It's just 10/60ths. 1/8, and so some of these other ones, I'll show you how I calculated out these different things. It's important for the Babylonians to not have a lot of repeating, like decimals, because their division process was equivalent to multiplying by the reciprocal. So if the reciprocal of these numbers were repeating, it would be complicated. So base 60 was really convenient for them in that way. I just wanted to show you how I calculated 1/9 into base 60. I just did an algebra equation, 1/9 equals x over 60, solve for x, and I got x is 6, that's 6/60ths, plus this 6/9, and I took that 6/9, turned it into 2/3, and then turned that 2/3 into 40/60ths, and that ended up being the 36/100ths place, because this whole thing is over 60 really. 1/9 is this many 60ths, so it's kind of like 6 over 60 plus 40 over 60 over another 60, or 6/40. That's there. So in base 10 that requires a repeating decimal, but in base 60 it does not. Babylonians had a lot of charts. I mentioned the reciprocal table already. They also had tables of squares of numbers, and they used them. Like for instance, here's an algorithm they had for multiplying two numbers together. So to do 26 times 19, they would add 26 plus 19, and they would do 26 minus 19, and they would square those, they would subtract them, and then they would divide the answer by 4. And as you can see here, 45 squared is 2025, 7 squared is 49, subtract them, divide by 4, and you do get 494, which is the answer to the question. And the question you have your students ponder is, why does this algorithm work? And you can think about that. You can pause if you want, or you could just see my explanation here. The Babylonians were aware of these sort of, whether they called it this, and this, they didn't call it exactly in this form, but they were aware of what we now look at, these are like 3 algebraic identities. You know, when you square a plus b, you get a squared plus 2ab plus b squared. When you square a minus b, you get a squared minus 2ab plus b squared. So when you subtract those things, the a squares and b squares cancel out, and you end up with 4ab. And here's 2 other sort of variations on this identity. And they really made use of it. So in this thing here, they're using the fact that a plus b squared minus a minus b squared is 4ab. So then when you divide by 4, it's going to be ab, which was the goal. So they use that identity. Now they solved quadratic equations in Babylonian math, and they found many tablets with actually some pretty complicated quadratic equations. But the most basic one is 2 numbers. You want to find 2 numbers that either add up to something, and they tell you what their sum is and what their product is, or in this case, what their difference is and what their product is. And the process was very similar for those sorts of questions. So this says, in a rectangle, the length exceeds the width by 7. If the area of the rectangle is 60, what are the dimensions of the rectangle? Nowadays we say x minus y equals 7, xy equals 60. And they did this a very clever way, which is equivalent to the quadratic formula, but they did it in a way that is almost more logical and easier to follow. Here was, first of all, I'll just show you what they did, and it won't be clear why they did this or why this works yet, but here's what they did. They started by taking that difference, that 7, dividing it by 2, then got 3.5, squaring that, getting 12 1/4, adding that to the product, which was 60, to get 72 1/4, taking the square root of that to get 8.5, and then adding that 8.5 back to the 3.5, which was 7 over 2, to get 12, and then subtracting the 8.5 minus the 3.5 to get 5. And those are the answers to the question. It's 12 by 5. Those are the numbers that have a difference of 7 and a product of 60. Why this works? Well, the 3/2, you give an x minus y, so the 3/2 is x minus y over 2. Then they square that, and this third line is the interesting one, that when you square x minus y over 2, adding xy turns it into x plus y over 2 squared. It's kind of like one of these identities. And then they take the square root of that. So now they started with x minus y over 2, and by using this line here, they ended with x plus y over 2. Well, if you add x minus y over 2 plus xy over 2, you get x, and if you subtract them, you get y. So it's very cool, it works, and it's dependent on that identity. These quadratics can get more complicated. Here it says the area of a square is reduced by 7 times the length, and the result is 60. What's the length? So that looks like this. X squared minus 7x equals 60. But if you factor out that x, it turns into x times x minus 7 equals 60. And if you call this x minus 7 y, well, you end up with the same story as before. xy is 60, this is x, that's y, and x minus y is 7, which they can then solve that way they did before. And it can even get more complicated. If there's a coefficient in front, they would multiply through by that coefficient to turn this equation to 9z squared minus 21z equals 60. Then they rewrote the 9z squared as 3z and squared that, and rewrote this 21z as 7 times 3z. And if you call 3z x, what do you end up with? Again, x squared minus 7x equals 60, which turns into the equation we've been working on. xy is 60, x minus y is 7. So x becomes 12, but x was 3z, so z is 4, which is the answer to this question. And they actually have like some really involved, there's many questions that go beyond this. I could do an hour just on quadratics, Babylonian quadratic equations. If you like this, you can definitely look them up. British Museum 13901 is the tablet with all the quadratic equation questions. They get really complicated with fractions and things like that. Plimpton 322 is the most famous mathematical artifact from this period. It looks like this, and translated it looks like that. It's a little hard to see, but what it ends up being is there's a list of Pythagorean triples on this Plimpton 322. The first one is 119, 169, which is Pythagorean triple, 119, 169, 120. The second one is 3,367. Hypotenuse is 11521, and the other leg is 11018. So you have these, some of them are giant, some are small. It turns out there's really a decimal point in front of all these because they didn't have a decimal point back then, so you have to tell from the context. This has been studied and analyzed so many different ways. Some people thought that they maybe had invented trigonometry back then because if you find the angle formed by these Pythagorean triples, if you actually make triangles out of them, the angle goes up by about 1 degree each line. But the most modern interpretation of it is that they had a recipe for creating Pythagorean triples based on this fact up here. This is kind of like that thing from before about how x plus y squared minus x minus y squared equals 4xy. This is, if you make y 1 over x, you get this identity on the top left, which if you divide by 4 and then put the 4 into the parentheses, you get this identity. Well, these are Pythagorean, this is a Pythagorean triple. One's a perfect square, this thing's a perfect square, this thing's a perfect square. So remember, they were good with their reciprocals, so all you needed was a number whose reciprocal was not repeating, two numbers whose neither the number or the reciprocal are not repeating decimals. So all we'd have to do is make the hypotenuse x plus 1 over x over 2, and the leg x minus 1 over x over 2, and the other leg would be 1. Now you just want to make sure that x and 1 over x are terminating, which in base 60 is easy to do because there's so much fewer, there's so many more terminating decimals. So I just did an example here. If I make x 5/4 and 1 over x is 4/5, and if I add them and divide by 2, I get 41 over 40. If I subtract them and divide by 2, I get 9 over 40. b is 40 over 40. It's a Pythagorean triple with fractions, but if I multiply everything through by 40, I get 9, 40, 41. The next country that we studied is China, and there was a major book written right around the time of Euclid's Elements, which is about 300 BC, called The 9 Chapters of the Mathematical Arts, and it has 9 chapters, and it covers different types of math, and the 9th chapter is about the Pythagorean theorem, which back then was called the Go-Gu theorem. Go and Gu were the names for the 2 legs of the right triangle. And they have, in this 9th chapter, about 24 different questions that can be solved using the Pythagorean theorem, different word problems, and a lot of them are not ones that I was very familiar with. We nowadays have like the ladder and the kite with the string, but these questions were very interesting. I'm just going to show you a sampling of some of them. In this one, here's a diagram from an old Chinese book called The Broken Bamboo Problem. The bamboo is 10 chi high and it's broken so that its tip touches the ground 3 chi away from the base. What's the height of the break? And as you can see, this is a question where the hypotenuse is 10 minus x and the one leg is x, so those add up to 10, and 3 is the distance of the tip of the broken piece to the base. And as you can see, the x squared terms cancel out. You get x equals 4 and 11 over 20, which is the answer. There's all kinds of different questions. I recommend you take a look at the chapter 9 of the 9 chapters. Here's another one which really surprised me. It says we have a tree that's 20 chi high and 3 chi in circumference, and this vine winds around it 7 times from its root to its top. Tell what the length is the length of the vine. And it's pretty interesting. You have the spiraling vine. Well, take a look at what happens if you what I have here is an animation where I'm kind of unraveling the vine. As you can see, it makes a right triangle, and one leg of the right triangle is the 20, which is the height of the tree. The base of it is the circumference times 7, since it wounds around 7 times, so there's the 21. And this is basically a question of find the hypotenuse of a right triangle where the sides are 20 and 21 and it's 29. That's a nice Pythagorean triple, 20, 21, 29. Anyway, there's many other questions that have different sorts of given information, like they tell you the sum of the 2 legs and the hypotenuse, or the difference between the 2 legs and the hypotenuse, and it's a good source of questions when you're teaching the Pythagorean theorem. One of the great Chinese mathematicians, somewhere around 250 AD, was named Liu Hui, and he's sort of legendary Chinese mathematician. He wrote a commentary about the 9 chapters, and that commentary is a very famous book, and he wrote essentially an extra chapter which has these problems in navigation. And you recognize these problems from trigonometry nowadays, where you have the sort of inaccessible object. They want to know how high up this sea island is. And nowadays we do this with trigonometry, and we know like the angle of elevation from the 2 different points. But listen to, in this question, we have these 2 sticks that are, or poles, that are these 5 bu, or bu is how you pronounce it, 5 bu high. And since they don't deal with trigonometry and angles, they say that the poles are 1,000 bu apart, and they also tell us that if you move 123 bu away from the bottom of this pole and you're on the ground, you look up, the top of the sea island will sort of correspond or coincide with the top of the pole, whereas for this one you have to step back 127 feet or 127 bu for the top of the sea island to correspond. So the given information is the distance between the 2 poles and the how far back from each pole, and the heights of the poles, and how far back from each pole you need to be. So it's an interesting question to try to do with trigonometry. You use tangent, and it's a famous question that it's a pretty ominous looking sea island. Anyway, here's the picture. This is an actual picture from one of these books, here's the information superimposed, and here's just that information. So without trigonometry, you can do a lot with similar triangles. And notice how you know the 5 and the 123. In essence, you know the tangent. You have the tangent of this angle, whatever it is. It's 5 over 123, and the tangent of this angle is 5 over 127. So using similar triangles, you can solve this. Liu Hui came up with a formula, which is just this. Height is BD, B being the height of the pole, D being the distance between the two poles, over A1 minus A2, which are the difference between these two distances, and it gets us the exact answer, 1255. In China, they have a lot of questions where they've done the square root, and they had a nice algorithm for square root that gets you individual digits of square roots. Even if they're irrational, you can get as many digits as you want. This algorithm used to be taught in elementary schools and middle schools in the United States, but it's something that was removed from the curriculum. I don't know when exactly, but here's the process, at least the algorithm. We take this was a 4-digit number. It's got a 2-digit square root, so we split the number into 2 groups of 2, and if it were a 3-digit number, we'd still make it 2 groups of 2. We put a 0 before the first digit. We take the square root of 13. 13, since 30 squared is 900 and 40 squared is 1600, square root of 13 is between 3 and 4, and we put the smaller number, the 3, above the 13, and that's because we're basically saying the answer is 30 something. Now, you may have seen this before. We double the 3 squared is 9, subtract, and bring down the next 2 digits. Now we double the answer so far, which we double the 3, we get 6, and we try to answer the question to get the next digit. 60 something times that same something is less than or equal to 469. And it's going to be a fairly large number. It's not going to be like 61 times 1. So I just went backwards from 9. 69 times 9 is 621, which is too big. 68 times 8 is 544, which is too big. But 67 times 7 is 469, which is the right answer. If you divide 469 by 60, you get about 7, so that actually would have been a good starting guess. Anyway, the 7 goes up there, and it works out perfectly. Geometrically, there's a nice visualization for what's going on with this, why we doubled that 3. So the area is 1369. Using multiples of 10, 30 times 30 is 900, so we chop that out. That leaves the 469. Remember the 469 from here. So this L-shaped thing needs to have area of 469, but that L-shaped thing could be broken down to 30x, 30x, and x squared. And there's the sort of 2, when we multiply the 30 times 2, here's a little, that L-shaped thing is 30x plus x squared, which is 60x plus x squared, and you factor out the x, it's 60 plus x times x, which is exactly what we did before. With a 6-digit number, it's going to have a 3-digit answer. We do a similar thing. It's between 200 and 300, or square root of 5 is between 2 and 3. Square it, subtract, bring down the next 2 digits, double the 2 to get 4, so 40 something times something is going to be close to 161. You want to get an approximation, just divide by 40, and it's going to be 161 divided by 40 is bigger than 4. The answer is either 4, or if that's too big, try 3. So 44 times 4 was too big, but 43 times 3 is 129, which is the closest that we can get. That gives us that remainder. So 3 is our next digit. Now we double the 20. The 129 goes under the 161. Subtract, get 32, bring down. Now don't just double the 3, double the 23 to get 46. 460 something times something is 3269. To get an approximation, you can do 3269 divided by 460, and that was 7, so you try 7, it worked out perfectly. This has a more interesting or more involved geometrical picture. I'll just put the picture up of what's going on with that. So there's a nice approximation of the area of a circle in the 9 chapters, where they say the area of a circle is the square of the radius times 3, which is like saying that pi is 3. Leo Hui does better than that and comes up with a method of getting a really nice approximation. And here's the idea. An inscribed hexagon is 6 times this equilateral triangle AOB. So inscribed hexagon has area of 2.598. If I want to get a better approximation, I can draw in this angle bisector. I have this triangle. Oh, by the way, this area you can get just with call the base AB and draw in the altitude. Use 30, 60, 90 rules. But to get the area of a dodecagon, a surprising way of doing that, an easy way of doing it. I'm not going to call CB the base and figure out what the altitude is from CB. Instead, I'm going to call CO the base. This circle has radius 1, and that makes DB the height of that green triangle. And since AB was 1, part of the equilateral triangle, DB is a half. Area of that green triangle is 1/2 times 1 times a half, which is 1/4. Multiply that by 12, and that thing has an area of 3. And Leo Hui says that that's probably why they used 3 times the square of the radius as their approximation for the area of a circle. And yes, we could get more sides and get better approximation, but Leo Hui does something I think pretty clever, which is at this point we know that pi is bigger than 3. But what's it less than? Well, that seems like it should be an involved question, but he does something I think very clever. Look at this picture here. So I've just added on. We see here the blue hexagon and these rectangles now outside the hexagon. They're part yellow, part orange. And he says that the circle's area it's bigger than the 12gon, but it's less than this shape, which is like a hexagon plus these 6 rectangles. So here's what he figures out. The 12gon minus the hexagon is the 6 orange triangles. And notice these rectangles. These rectangles have the orange triangle in them. They also have these 2 yellow pieces. Well, the yellow pieces are equal to the orange triangle put together. So the 12gon minus the hexagon is not just 6 triangles, but it's also 3 of those rectangles. So 2 times the 12, if I double everything, the 6 rectangles area together is 2 times the 12gon minus 2 hexagons. So pi down here is bigger than the 12gon, but less than the hexagon plus the 6 rectangles. But the 6 rectangles are 2 times the 12gon minus 2 times the hexagon, and he gets this nice identity. Pi is pi is bigger than the 12gon, but less than 2 times the 12gon minus the hexagon. And I don't have it here, but I will when I do my presentation. That gets us, it's between like 3 and maybe 3.2. And then when he goes one step further and does something like this for the 24gon, he gets a really nice approximation of pi. Chinese remainder theorem is a question about finding a number that gets us different remainders when we divide by different things. So the emperor secretly counts his soldiers. When he counts his soldiers in groups of 3, 2 soldiers are left. When he counts in groups of 5, 3 soldiers are left. When soldiers count in groups of 7, 2 soldiers are left. So he's saying when you divide by 3, you get remainder 2. When you divide by 5, you get remainder 3. When you divide by 7, you get remainder 2. Nowadays, we say the question this way. And it's called the Chinese remainder theorem. It actually has practical application in astronomy when they want to know when will these celestial objects be in the sky in this configuration again, if we know sort of the period of each one. But as a riddle here with soldiers, it's an interesting question. The answer to the question is 23. And here's the way they came up with an algorithm for this sort of question. First, we find a multiple of 5 times 7, which is 35, which is 1 more than a multiple of 3. And that ends up being 2 times 5 times 7, or 70. Then, for the middle equation, we find a multiple of the other two things you divided by, a multiple of 3 times 7, which is 1 more than a multiple of 5. Well, 7 times 3 is already 1 more than a multiple of 5, so 1 times 7 times 3 is 21. And a multiple of 3 times 5, that's 1 more than a multiple of 7. Well, 3 times 5 is already 15, which is already 1 more than a multiple of 7. Multiply the 3 remainders by the 3 numbers and add together, and then divide by 105 and take the remainder, and that's the answer to the question. Let's see why that works. So this is the remainder I want when I divide by 3. This is the multiple of 35. That's remainder 1 when I divide by 3. This is the remainder I want when I divide by 5. This is the number I get. This is the multiple of 3 times 7. That's remainder 1 when I divide by 5. This here is the 2 is the remainder that I want when I divide by 7. 1 times 3 times 5 is the number, the multiple of 3 times 5. That's 1 more than a multiple of 7. And this here is, if you divide this big number 233 by 105, it's like subtracting, and you want the remainder, it's like subtracting away 210. So why does this work? Well, look what happens when you divide by 3. Because there's a 3 in these 3 terms here, you can kind of ignore them, and you're left with just this. So when you divide by 3, these 3 terms that are covered up don't alter the remainder, don't affect the remainder. Now 2 times 5 times 7 was the special multiple of 35 that leaves remainder 1 when I divide by 3. So if I multiply that by 2, I'll get remainder 2 when I divide by 3, which is what I want. Over here, when I divide by 5, the first, third, and fourth terms don't affect the remainder because they have 5 in them. So all that matters is the middle term. 1 times 3 times 7 is remainder 1 when I divide by 5. So if I divide by 3, it becomes remainder 3 when I divide by 5. And finally, this is the only term that matters when you divide by 7. And 1 times 3 times 5 has remainder 1 when you divide by 7. So doubling it gets me remainder 2 when I divide by 7. And that was the goal. Now coming up with these 3 numbers is maybe an issue, but if you can come up with those numbers, there's various ways of doing that. This is what you do with those numbers. That's the Chinese remainder theorem. Chinese remainder theorem is named the Chinese remainder theorem, so they're given credit for it, unlike Pascal's triangle, named after Pascal in the 1600s. Here's his version of it, whereas in the 1300s we have this picture of the so-called Pascal's triangle, and even in there they say it's been around for a long time, hundreds of years. The final culture that I studied was India. Here's a nice proof of the Pythagorean theorem. I really like it. I forget now what year this is from, but it's called the Behold proof because it's when it was published, they just had this picture with the single word behold. It's not that clear what's going on. You have these 5 pieces down here on the left, and you have sort of the same 5 pieces on the right, but it's not clear what this has to do with the Pythagorean theorem. They didn't have color back then, so the word behold said it all. They didn't publish in color. When I click, you'll see why this was worthy of the one word behold. 1, 2, 3, boom. As you can see, the bottom left is c squared. the hypotenuse, a square on the hypotenuse, and this L-shaped thing is actually a squared plus b squared. You can definitely have fun with this and have students try to figure out from this picture, and even after they see it, to try to talk about how do we know this really is a squared plus b squared. That's a real neat little proof. The Indians had a approximation for the square root of 2, and this is actually on Wikipedia as 577 over 408, which is very, very close. But it's written not as 577 over 408, but as 1 plus a third plus 1 over 3 times 4 minus 1 over 3 times 4 times 34. And in this representation of 577 over 408, there's an algorithm suggested, and maybe there's even more terms to make it more refined. I'm going to show you a geometric interpretation of how they might have gotten this expression. So here are two squares that have area 1, and we want to assemble, sort of cut them up like a jigsaw puzzle and create a square of area 2. And that can be done very easily, like that. But that doesn't, and so this square on the bottom has area 2, and its side is actually the square root of 2, which doesn't really help us calculate it, but it is a cool picture. To actually get something that we can approximate with rational numbers, here's another way of taking the two squares. So here I cut up the top square into two pieces, and it's made this L-shaped thing. That L-shaped thing does have area 2, but it's not a square. But we know the height and width of it are 1.5. And this means that the square root of 2 must be less than 1.5. If you filled in this little square here, the area of that would be 1.5 squared, which would have an area bigger than 2. So we have an upper bound on the square root of 2. We can get more clever. Check out this pretty awesome picture. To cut up the top right this way, the Indians did this, and they ended up with the pieces fit together into a L that's more like a square, and the height and width of that is 1 plus a third plus 1 over 3 times 4, or 17 over 12, which is a better approximation, but still it's too high. So where does that extra term come from, that correction term? Well, let me go back to the 1.5 by 1.5 thing with the L missing. This thing has an area of 2, and the idea is to cut a sliver off of the left-hand side and off the bottom side in such a way that they would sort of fill in. So if I could take a sliver off of here and make it just the right size so it would fill in half of the missing hole, and for that to happen, I could solve this equation. 3 halves x, this is the width of the sliver, is half of the hole. The hole is 1/2 squared. We get x equals a 12th. So if I did that, I cut off this 1/12 slice, I could fill that in here. And if I do it on the bottom, well, I can't actually cut an entire slice off because this piece on the bottom left has already been cut off. But I could fill that in like that, and that actually gets me the 17/12, which was that other approximation. Well, if you do this process again, where you figure out what size sliver do I need to cut off of this 17/12 so that that rectangle would fill in half of this little guy, I get 1 over 408. And guess what? When you subtract 1 over 408 from 17/12, you get 577 over 408. And that's our 577 over 408 answer, which is also 1 plus a third plus 1 over 3 times 4 minus 1 over 3 times 4 times 34. Gregory Leibniz gets credit for the arctan formula, but that was invented in India hundreds of years before. The last thing that I'll show you is the great Ramanujan. He's a modern mathematician, 1887 to 1920, so this is not ancient. But he died very young. He was a self-taught mathematician who sent his work to England, and Hardy discovered him or invited him to England, and he came and they worked together, and Ramanujan died very young, but Hardy says he was maybe the best mathematician that ever lived. A neat story about Ramanujan is that while he was in the hospital, Hardy said that his taxi cab number was boring, 1729, and Ramanujan instantly said that 1729 is very interesting because it's the sum of two perfect cubes, smallest number, that's the sum of two perfect cubes two different ways. And that's a nice riddle to ask students to try to find, give them a list of perfect cubes and find a number that's the sum of two perfect cubes two different ways. Squaring the circle is using a compass and a straight edge to find a square, the length of the side of a square that's the same area of a given circle. Ramanujan, one of the few things that that high school students can understand from Ramanujan is this proof where he has a circle and he draws this point T, which is 1/3 of OR, and he draws an altitude and makes another line segment the same length as that altitude, and creates this right triangle and makes a couple of parallel lines. This PM segment he copies to make this PK. He draws this perpendicular line and draws all this stuff, and ultimately ends up with line segment RD. And if you make a square on RD, it will have almost exactly the same area as the circle, so it's a very short construction to almost square the circle, and it works because pi is very close to 355/113. Well, that is the end of the presentation. I'll put up more videos with more stuff that I left out because I wanted this presentation to be an hour, but I hope you liked what you saw. Again, the Katz book, Victor Katz, is a big $70 book that has enough stuff to keep you busy for a couple of years. The Crest of the Peacock will keep you busy for a few months for sure, and then I will, on my GaryRubenstein.com page, if you go there, I'll put extra links with handouts and lessons that I've made and worksheets and things like that. So I hope you enjoyed this tour of the history of 4 cultures. That each of these cultures I could easily do several hours about, so to do 4 in an hour is definitely cutting short what these cultures deserve, but I hope this gives you some stuff that you can think about and introduce to your classes. Thanks for watching.